Hey team, so here is our topic. We're looking for equilibrium concentrations. All right, how do we do it? This is the math. All right, now here's our objective, what we want to figure out. Particularly the word is calculate. So we're going to do some math today. And Dr. Square is like, he knows his K values and his initial values, and he wants to know some final value. Now, one thing to be this and this is something that I've kind of made up, not made up, but the way I've written it is probably not the way it's going to be written in the problem. However, I just wanted to give you an idea of what these problems were about or what they were like. All right. And this is another way to look at the problem or think about the problem. He knows how much he starts with these two things, these two chemicals. He knows his K value. He knows his equation and he wants to figure out, hey, how much of this at the end do I have, or more so at equilibrium, all right? Which in this case would be final. To do these kind of problems, we're going to use what is known as an ICE table. And an ICE table is basically a table where you're going to chart your species that involved in the reaction. And these species also need to be in your equilibrium equation. And you're going to put you're going to write ICE down here, where I stands for initial, C stands for change, and E at the end. All right. And I want you to have a good, please get this like just a blank one so you can refer back to it. All right. All right. When we do these, there are three real methods to do them. The one is where you neglect the X, and this is really for a small K value, meaning your forward reaction almost doesn't happen. The other is called the perfect square, and the last one is the quadratic. Now, this up here, this X, we're not going to do this in this video because it's very uncommon on the AP. So I'm going to not go over it. All right. Here's our problem. Now, the first thing we want to know is our equation. I read the problem. Boom, nitric oxide, that, and that. Those are my reaction, my species involved in the reaction. And I'm going to write an equation. Well, it's going to be N2 plus O2, nitrogen N, monoxide O, and I'm going to need two of them. All right, here it is. All right. Now I'm going to set up my ICE table. Well, N2 was going to go there, and O2 was going to go here, and O2 was going to go there. NO was going to go over there. All right, you don't put any coefficients with them. Now I put my ICE down here, and I read the problem. I see I start with both 0.02 molar. Oh, that should be 0.2. It isn't. It should be 0.2 right there. See? And I don't start with any of the product. Now, to get the change, you got to look at your coefficients. All right, what's the coefficients here? They're the same. So whatever change X is going to affect them both equally. It's going to be negative X. Since this is a 2, the change will double against the nitrous oxide. That's what I was trying to say. And the equilibrium amount will be this for each of them. All right. Now, the next thing to consider is, or next thing you need to know is my equilibrium constant. No. My equilibrium expression. And that's going to be my products, the concentration of NO2 to the squared, all right, multiplied by those two. And we're going to plug in to them. These two are going to go there and there, and this is going to go there, all right? So this goes there, that goes there, and that goes there. And I get 2, and that would be my equilibrium expression. Now, here's my equilibrium expression. The next thing we need to consider is which method we're going to use. You need to know your k value. If you in the problem, the k value was this. You can see that this is a lot. It's about 1,000 times greater than this. So we're going to have to hope and use the perfect square. Is this a perfect square? The answer is yes. So we can use this method. All right. And to do the perfect square, the first thing you're going to do is take the square root of things. All right. This side will simplify to that, and this side will this will get canceled, and the bottom will be reduced to that. All right. Now, to solve this, the first thing I'd want to do is get rid of this fraction. So I'm going to multiply both sides by that factor. It's going to cancel on the right, and I'm going to be left with this on the left. And that's going to be this. It's going to simplify out to that. The next step is to distribute this to each thing. All right. I'm going to get this. And then the next step, I want to isolate x, combine like terms. I got to do that before I isolate x. I'm going to add this to both sides. I'm going to be left with this. And now to isolate x, I'm going to divide by that. And I get this. Now you may think you're done, but you really have to go back to your ICE table and use this to predict these concentrations based upon your equilibrium expression in terms of its change. So I'm going to substitute it in. All right. Then I'm going to round and I get this. Oxygens is going to be the same. All right. And NO behind my face is going to be that. And that is the answer to my problem. All right. Now, I'm going to cheat a little bit. Let's say I varied the temperature and I got this K value. Now you can see it's significantly less. All right. And it is less than this factor. So I can use neglect the X. Oh yeah, love it. And solve it using this way. And my answer is not going to come out the same because my K value is appreciably different. I should have much higher concentrations of the reactants in the end than I did in the last problem. So I substitute in and now I'm neglecting the X. And when you neglect the X, you're mainly dropping these two things right here because you're saying that they're so small it doesn't really matter. All right. And this would essentially become this. All right. Now, at this point, there's lots of things I could do. I could do my laundry. I could probably put more wood on the fire, but I'm going to decide to square both sides. All right. And this is going to simplify to that and this. The next thing I'm going to do is multiply both sides by 0.2. All right. These are going to cancel, and this is going to be that, and I'm going to divide. And here's my change. All right. Or not change, but here's the factor that I can use to figure out my equilibrium amounts. I'm going to substitute them back in, and you'll notice that this has really changed very, very little, and almost if you round, it hasn't changed at all. And just like that. All right. Thank you, and I hope you have a good day.